Hello guys, today we're going to be doing the first lecture of ITE, which is the Information und Nachrichten. So let's go ahead and begin. We have these definitions, we have this index, the Inhalt dieser Präsentation. It's not really that important, so we can just skip it. So the first thing we're going to be looking at is Nachricht. So I put as you can see, I have a little image of a phone here. And that's because that's the best way we can represent a message nowadays. I think it's a really analogous example to understand what a message is like. So for example, if I go here and I want to send a message, I have to write characters, right? Certain characters, and I have to continuously write these characters up until I'm done. And once I'm done, I press send, right? This is just basically saying, hey, our message is made out of characters, meaning Zeichen, or continuous functions, which is also in this case continuous functions when I write. Me writing is a continuous function in a sense. So I can just write the message continuously, and that will be my actual continuous function, so to speak. Just quick thing, I'm sorry if I just have a lot of boogers today. I have a lot of allergies. It's like spring season over here in Mexico. That's why I'm getting all this allergies. So yeah, I'm sorry if I'm just kind of sick sounding and just allergies. So let's continue on. We know that a message is built out of Zeichen or continuous functions, as you guys can see in this little example here with Jane Smith. The most important thing of a Nachricht is it has a characteristic that it represents information. So we can Informationen darstellen, ja. And sie dienen in erster Linie der Übertragung und werden daher als eine Einheit betrachtet. The main focus of a message is to send it, to share it in a sense. So that's pretty much what it is. Its first main focus is the Übertragung of this said message. So we can say, what is a message? A message it can be consisting of Zeichen, data, or symbols, right? So for example, if we go with a data example, data is organized information that is ready to process. Let's say you go to an example. Let's say you go to the supermarket and you go to Rewe or Aldi and you have your Einkaufsliste, and you have a list, and you can process this list to say we need eggs, we need bread, we need keine Ahnung, Lebkuchen, Leberkäse. Yeah, that's all your four things that you have to bring, and you can process these things, and use this data and process it. Data can also be created as a result or as a way to process something. So in the case of our list, we will create the list just to process it, but sometimes we can also want only the result of it. So maybe, for example, you want to list all the things you have in storage in a room. So you write everything in the list. Like I don't know, imagine you open your fridge and you have, okay, I have some butter, I have some ham, and I have some broccoli. And that will be your Ergebnis or result, because you just want to keep this result. There's also different formats and types of data. This is quite evident because if you go to any computer, you can get a lot of formats and types of data. Sometimes the data is going to be an image, sometimes the data is going to be a list, and sometimes the formats of these are going to be unterschiedlich, different from each other. So for example, in images, you can use PNG or JPEG. In text files, you can use text or docx, which is a Word format. Data can also be created, it's created by characters, Zeichen, or continuous functions. So now let's go with Zeichen. What's a Zeichen, right? It's quite interesting because at the beginning of the lecture, I was like, what the hell is the difference between Zeichen and symbols, right? What's the actual difference? Well, the actual difference is that Zeichen are just objects, gestures, or marks that give out information, but that by themselves, they don't have any meaning by themselves. Zeichen are just an element of a finite set of things. For example, a perfect example would be our Zeichenvorrat or alphabet, or for alphabet, we have A, B, C, D, E, F, G, and it goes on and on and on. It's a finite set, and an element of whatever of this set is going to be a Zeichen. However, you have to take into consideration, let's say we take A by itself doesn't really mean anything. And that's what a Zeichen is. A Zeichen is just a mark that you write, but that it by itself, it doesn't have any actual meaning. It doesn't really give you any information. However, if you have a combination of this Zeichen, you can create something. So for example, we can write CAB, which translates to cab, and the cab is basically a taxi. Or we can write DAD, which would be dad, right? So let's say, imagine I'm texting a friend and I send just B without context. It doesn't mean anything, right? But if you write dad, oh, now you have the image of a person who's a dad. Let's continue. Now symbols are quite similar to Zeichen in the sense that they're just something that are visual. However, they're abstract ideas or concepts that can be just processed through a little symbol. For example, it says here, sie werden häufig verwendet, komplexe Bedeutungen auf prägnante und effiziente Weise zu vermitteln. Examples were symbols or flags, logos, emojis, and Verkehrsschilder. For example, an example of these will be the plus, the minus, and the division and the multiplication signs. I know it's a bit confusing because I added these over here, but that's an error of my part when I was doing these Folien. So just ignore that. It's mostly this little symbols, mathematical symbols, are actual symbols, not Zeichen. Basically, oh my gosh, I cannot breathe. So basically, you have the plus and minus, division, multiplication, and the plus and minus have all these symbols have abstract ideas. By themselves, you can create something in your head. So you have 3 and then plus 2. It means you're adding 3 and 2, and so this plus is a visual representation of whatever concept you want to add. Another example would be the saving icon. Saving a file includes a lot of steps in the computer. You have to allocate memory, not a memory, really a memory, like space in your hard drive, and then put a name of the file, and then save it somewhere, and it goes along a lot of steps. However, when you're in a computer, you don't see those steps. You will normally back then you would write something in the command line, but nowadays you just have to press a little save icon and you're done. The save icon in this case stands for an abstract idea of saving something, right? Let's continue. This is pretty easy. It's just physikalische Größe als Nachrichtenträger. It means that there's whenever we have we can use physical measurements to use as message holders in a sense. So for example, we have Gewicht, and the Gewicht has a Betrag. So for example, we can say 23 kilograms. 23 will be the changeable parameter, and kg would be the actual Gewicht. It's pretty simple actually. Now we're gonna go with the signals. These are the signals, so we're gonna go one by one. Let's continue with this one, the kontinuierliche Signal. This is theoretical, as we cannot really create a signal out of this. By meaning a signal is something that changes. So for example, let's say we have a sign that something is on. Let's say if you want to have a sign that something is on, you need another sign for something that's off. And over here, there's no way of creating any type of sign because we have no lines going on the y or x axis to create this signal. So it's not really applicable here. It's therefore theoretical, and it's not really doable here. However, if you can see here, we have a zeitdiskretes, wertdiskretes Signal, and it focuses on the x-axis, as you can see. This graph over here, I'm not really sure if it's correct. I just read it really quickly on my iPad, so excuse me if it's wrong. But the gist of it is that you just focus on each line that you have here, like from here to here, and then from here to here, from here to here, and from there you can just start off doing your own signal. The next one will be right here, as you can see, the same title because I forgot to just change it. But this will be zeitkontinuierliches, and this will be wertdiskretes Signal. Over here, we're just focused on the y-axis. You see, quite simple. Now you may not understand this. Don't worry, we'll be looking into it later on in an exercise we're gonna do real quick. So don't worry. Over here, it's both of them. It's gonna be zeitdiskretes and wertdiskretes Signal. This is wrong, and this is taken as a digital signal, and you need intervals to find the actual signals. Okay, perfect. Now we have this. So let's continue with this. Signals with bounded number of values. If we have a graph and we want to find the intervals, we can find of a digital signal, we can do the following. First, we find how many digital signals we have. Then we're going to determine how big our undefined area should be. And with this two pieces of information, we can create now our intervals. So what does this mean? What does an undefined area mean? Well, undefined area is basically just, let me just show you, is this little like area in which is like the bridge between two areas. For example, this is area 1, this is area 2, this is area 3. And this is like the bridge between them. So let's go back. And it says we have this Aufgabe or exercise, and we want to do this graph, and we want to, in a sense, create an analog signal. We have an analog signal, and we want to convert it into 3-value digital signal. And der Eigenspannungsbereich des Analogsignals beträgt von 0 bis 2,5 Volt. And the undefined area should be of two digital values should be 1/2 of the interval of a digital value. First, they ask us to do the interval. Then, yeah. So let's continue. Let's actually do this. This is quite simple. First, you write your information, right? So the volts, and you know that undefined area is 1/2 of the interval of the actual digital value, and then we have 3. So now we know that we have 3 values. So this means, well, 3 digital signals. This means that you want to divide a little box into 3 little slots. To do that, you need 2 lines. As you can see, this red line over here, and this red line over this other red line over there. These red lines are going to be our undefined areas. So as you can see, we have 2 undefined areas, which are the bridges between all of the digital signals. So we have 2, and we know that each of them is 1/2. So we're going to do 3 plus 1/2 plus 1/2, we have 4. Now with this 4 number, we can divide it with our volts, and we get 5/8. What does this mean? It means that from here to up here, it means we have 5/8 of a volt, right? From here to here. So that's pretty much it. We got 5/8. If we multiply it by 3, we're going to have the full amount of volts of this first area, this second area, and this third area. Quite simple. Yeah. So basically, you can multiply by 3, and you get all the full thing of like how many volts the digital signal uses. However, you can see that we're missing 5/8 of a volt because this is divided into our 2 undefined areas, meaning this one and this one. So it means that we have 5/8 and we have 2 little undefined areas. It means we have to divide it. So we have 5/16, meaning that now we know how big our undefined area is. So we can start off with saying, okay, I know that my signal is going to be from 0 to 5/8, and then I'm going to add 5/16 to 5/8, and I get 15/16, because basically what we're doing here is saying, hey, this is 0 to 5/8, but this is 5/16, so I have to add 5/16 to enter the next block, and the 15/16 is going to be basically from here up until 25/16. And the number between these two guys is 5/8, because we know that this one is 5/8, this one is 5/8, and this one is 5/8. So that's pretty much how you get the thing, as you can see. And it's pretty simple. So now that you have your undefined areas, we can do the following exercise. Over here, we're going to start off with the zeitdiskretisierung. The zeitdiskretisierung should be on B, and wertdiskretes should be in C, because I just mixed it up. So we'll start off with zeitdiskretisierung, in a sense. Zeitdiskretisierung is really simple. You just go block, well, you have these little squares, you see. And you go square by square, right? And you start at the beginning of the square, and you see where the value is. So in this case, for example, we have this value enters over here. Oh, it's in the same digital signal that I determined. So I just write a line. And then over here, at the beginning of the second one, I'd see that it's over here, so it stays in the same one. And then same thing here, it's on the undefined area, but undefined areas are same as the last block, meaning it stays in the same one. Over here, same thing. But over here, as you can see, once we go down, it enters the next block. So this means it has to go down and then to the right again, right? And then it continues. If you can look at the graph, it goes like this, goes down because now it's in a new area. And over here it stays in the same area up until we go over here. You see? It's not that difficult. Just take a pause, rewatch the video of explanation right now, and you'll get it. Now the wertdiskretes Signalen is a bit different. It's quite easier actually in my opinion. You don't have to go over here. We went square by square, as you can see, but over here we're just going per value. So meaning whenever the value changes. So we say in this line up until it enters a new block. So we just say, oh, once it enters a new block, we go there, and it continues up until it goes here. Okay, and then it stays there. And then the graph goes again on the second block. So it goes up again and it stays there for its totality. And that's pretty much it. Now we're going to take a look at the question of why should we use binary? Well, binary is the most simple logic we can use. It can be yes or no, 0 or 1, low or high, 0 or 1. Low is, for 0, stands for 0, and high stands for 1. A binary signal is equal to 1 bit, a binary digit in English. And a binary signal is not enough to create representations of information. We need more representations made out of more binary signals. What does that mean? Well, let's go ahead and take a real quick example here. We have 16, 8, 4, and 2 combinations in relation to every single table here, respectively. So let's take a look at this first table over here, 0 and 1. Imagine this 0 and 1, this little function here, stands for our LED light, a LED light, LED, that turns off when it's 0 and on when it's 1. So when it's off, when it's 0 it's going to be off, when it's 1 it's going to be on, and perfect. We go to the next one. Look at this, we have even more states. So what I can do is say, hey, when it's 0, it's off, when it's 1, it's on, but when it's 0, 1, it'll make a blinking effect, and when it's 1, 0, it'll make I don't know, a pattern blinking effect. So it can make like on, off, on, or something like that. So in a sense, with these little boys, we can create different little states, so to speak. Over here, we would have even more flexibility to create more states, and even here, even more. Now, if you want to know how many binary slots we need, for example, for how many values we have, over here we count our values. We have 8, right? So if you write log 2 and then of 8, you get 3, meaning you need 3 binary numbers, well, 3 binary states, so as to create this table. That's pretty much it. Now let's go to the next one. Remember, this formula is important. And now for the last thing is a hysterese. My gosh, I'm so sorry, it's disgusting, but it's just my allergies, I cannot control them. Basically just like a loop saying, imagine this is a graph that controls the behavior of an electrical heater, and when you have input current, and it goes up to a certain limit, and we also get this flow, then it means that it'll stop heating, and it'll go back, turn off, and once it goes back to the same position, it starts all over again. So it's saying basically just do this up until you get to this point, and now go back to the original point and start all over again. And that's pretty much it. So thanks for watching this video, guys. I'll be adding the exercises on this drive. You can look in there. I'll also include a solution of the first exercise and the solutions for the theoretical ones, so don't worry. So yeah. Thanks for watching, guys, and I'll see you in the next video, I guess.